first of all, thank you. Thank you all for coming. Thank you for your remarks, kind, humor, wit, everything else. And anyway, you might recognize the skyline. That's our view from the beach on 4th of July at sunset. So we can see about 35 miles across the lake.
On a very, very.
And there's I mean, you can recognize the Willis Sears Tower. It's the big one on the left.
Wow.
Anyway, so this is thanks and some pictures and some icons and some other comments.
Because you haven't had time to prepare.
Yes. Okay. History. My history is a little complicated, and the thing about it is it isn't sometimes driven by science. It's driven by sort of events. And in where I start, I have to figure out which one of these. Is one of these things the light? I guess it's
top one.
Ah, got it. Anyway, I began at Cornell University as an undergraduate in chemical engineering. Now, it was generally recognized at Cornell at the time that the two most difficult courses of study was architecture and then chemical engineering. The architects were crazy. They just had to do what they did.
Well, they speak highly of you.
So after 4 years of undergraduate education in chemical engineering, I've got a BS degree in chemical engineering. And then, in my senior year, I did a class in synthetic inorganic chemistry, and the instructor was Robert Fay. And I applied to stay at Cornell in the graduate program in chemistry. And they allowed it because I was switching schools from the engineering school to the College of Liberal Arts and Sciences. So anyway, that's why I stayed at Cornell for 9 years in Ithaca, New York. By the way, Ithaca, New York in February is just plain awful.
Which is why you were so happy at Argonne.
Yeah, it was probably even worse than that. Anyway, so in 1971, I made an application to the National Science Foundation for postdoctoral fellowship to go work with F.A. Cotton at MIT, and was awarded the fellowship. I also just literally as a lark applied for a faculty position at Arizona State University. I simply did it as a practice. Went down there, did the interview as a practice, because I didn't think I was going to get that sort of a position. And lo and behold, I wound up getting the appointment to be on faculty at the chemistry department at Arizona State. And they said, well, it turned also that Cotton was moving from MIT to Texas A&M, and I really didn't want to be a postdoc there, spending all my time doing nothing but moving equipment from one state to another. That would have been just a waste of time. And the folks at Arizona State were really very, very kind, because they said, look, come to ASU, get your instrument. If they bought me that syntax counter, the single crystal diffractometer that somebody showed. Yeah, Jeff Post showed it. And so I had to come there, set it up, teach a class, and then go do your postdoc, but do it at Oxford with J.S. Anderson, who was professor of inorganic chemistry at Oxford. And so I said, sure, I'll do that. And so I guess you're sort of right around here someplace. So I arrived in Arizona in 1971. Now you have to appreciate that leaving Ithaca, where the temperature was like 56 degrees, and stepping off the airplane onto the tarmac in Phoenix's old Sky Harbor, where the air temperature was 108, was a bit of a shock in August. Anyway, so I went to Oxford, and basically the initial thing I was expected to do was to work on electron microscopy of tantalum oxides to see if I could recognize whatever the structures were. And it turns out I was really terrible at electron microscopy. I simply didn't have the eyes to do the focusing that you had to do at that time manually, really. And so one afternoon, Tony Cheatham, who I'd friends with, walked in and said, "Bob, how'd you like to do a neutron powder diffraction experiment?" And I said, "Sure." And so we did those things that he described, which is the titanium iodine oxides. By the way, those experiments were done at liquid helium temperature at a diffractometer that was at the Pluto reactor at Harwell, which is like 35 miles south of Oxford. So we had to drive down there to do the experiments. And each one took 3 days of data collection to get that data on a sample that was probably about that big around and about that high. It's like about that big. And Tony had this program that he had acquired from Alan Hewitt. And I'll show you the cover of Alan Hewitt's instruction manual in a couple of slides. So it wouldn't do those problems because those problems were too big. The computers didn't have enough memory to be able to increase the array sizes enough to handle the number of reflections that those two compounds generated. There were like 600 or 700 reflections, and the program was limited to about 300. So I had to actually rewrite the internal stuff in both of those programs so it would handle larger numbers of reflections. And it took a little while, but I did manage to do it. Then let's see. Then I got back to Arizona after doing all this, and then went back and visited Oxford, I think the following summer for a brief time. And in that period, Professor Anderson, or maybe it was right before I left, he asked me to be an applicant for this position that Tony referred to as a permanent faculty member at Oxford. I would have been flattered. And then that interview then occurred in 1974. Now, Tony just sort of mentioned it, but I'll add a little bit to what that interview was like. There were 6 candidates. Tony and I, 3 guys who were local, who were literally space fillers. They wanted 6 candidates, so they went out and got 6 candidates from the local postdoc community, and 1 preferred candidate that came from the US someplace. And I won't say who he was or where he came from. So anyway, he was apparently the candidate that they had wanted. The interview was all in one day. All 6 of us were interviewed at the same time in one day. The university part of the interview was in a room almost as big as this, with one big table in the front where I was standing behind it, and this huge crowd of people, about as many as are you here, all firing questions for maybe 20 minutes or a half an hour or something like that. That was the university interview. The college interview was a dinner at High Table at Christ Church College. pulled out all the stops for this dinner. They brought out the gold plates, the fancy stuff. And it turns out that we drank the place dry. They actually someone apparently had to run out to the nearest odd tins to buy a bit more alcohol for this party. And the preferred candidate, unfortunately, got drunk. And then I went back home after all that and got this nice letter from Professor Anderson telling me that Tony Cheatham was chosen by the college and I was chosen by the university. The college takes precedence over the university at a place like Oxford. To me, that was the perfect result because I would have been a fish out of water at a place like Oxford. Not used to I would not have any idea what to do with that system of tutorials and all that sort of stuff. The way they do education. I probably could have figured it out, but it was best that Tony did it rather than I did it. Anyway, so that's the story of that. And by the way, that interview has gone down in the history of Oxford as being one of the sort of more memorable events in a university that's 600 years old. People still remember that interview. Anyway, so I'm back at ASU, got promoted to associate professor and then eventually to full professor. And in about 1980, which is, there was no record, I did do a trip to Rutherford Lab, a sabbatical, where I worked out the peak-shaped business for the neutron atomic flight patterns, using that same code. And one other thing I should say about coming back from Oxford the first time is I came back with that Rebuttal code that I had worked on. And when I was working on it, I put in something to try to do X-ray diffraction. K alpha 1, alpha 2, things like that. And it was Gaussian peak shapes and it didn't work. It would not fit the line shapes to get out of an X-ray powder diffractometer. And of course, there were no modern powder diffractometers. What I was trying to use was an old GE flat machine. A handful of you may remember what these things look like. It was in the geology department at Oxford. It couldn't get it to work to anybody's satisfaction. So I brought the code back and handed it to Ray Young. I said, here, this is your problem, sort it out. And he and his postdocs and graduate students went through a whole lot of different kinds of possible line shapes and finally settled on whatever it is we now use, which is Lorentzian and Gaussian mixtures of some sort. And that code then wound up being the basis of all sorts of other Rebuttal refinement codes. So, including full prof. And full prof got it because when I was at Oxford, I think the second time, I went to the ILL. In fact, actually, it was the first time. We all went to ILL for one of the very first British explorations into neutron scattering at the ILL. And it was it was Tony, myself, and Brian Fender went there to do some of these experiments at the ILL. And I brought along a magnetic tape. Now, there's a funny little story about that. And I had a magnetic tape and print out a whole bunch of stuff in my briefcase. And I went by the night train over on the ferry across the English Channel, and then on the train to Paris, where you then had to change trains to get the train to Grenoble. Well, as soon as I got off the train in Paris, I was met by a gendarme and an inspector who wanted to know what I was carrying in the briefcase. because they thought I was an industrial spy. They opened up my case and took a look at it and saw, germanium, niobium oxide, and he says, oh, okay. Oh. So, almost got arrested for spying in France. Anyway, that code was then delivered because it was on that magnetic tape, to the people at the lab. And somehow that wound up in the hands of Juan Rodriguez Argonne, who then created FORTRAN. So you can see what the parentage and grandparentage is of many of these belt refinement programs. And I have a feeling I sort of dabbled in some of them. And you can recognize them because the control files for these things are basically Riefeldt's original thing. Paul uses his terminology and usage. Yeah, where am I? Somewhere around in here. Well, I did go back to the Neutron Beam Research Unit. These are the people who were putting together the proposals and everything else for what was now known as ISIS. There had been nothing built. They were just simply putting together all the paperwork for it. And anyway, I worked out what those peak shape functions were, and there had been a report from the Department of Energy at that time that said spallation sources won't work because no one can fit the peak shape. Peak shape is an impossible thing to fit because it's way too complex and messy. So there won't be any powder diffraction, therefore there's no reason to build spallation sources. Well, then this paper came out and showed that that was incorrect. So I suppose in some sense I saved spallation sources from an early extinction, but anyway, I'll pat myself on the back for that. Anyway, and I brought that code back, and that got handed off to Jim Jurgensen and Frank Rotella, who then used that as the basis of the codes used at IPNS for belt refinement. After that code.
Used it. I used it.
And you used it right now. Everybody used it at the time. Then in 1980, I started going to Los Alamos in the summertime, basically to escape the heat and do something that I could get paid for. And so I was a summer contractor at Los Alamos, helping them with their neutron scattering program. And in that process, Richard Silver, who was the group leader at the time for Lance, asked Alan Larson and myself to write the software to support the single crystal machine and the powder diffraction machines. Now, what was in Richard Silver's mind is each of us would individually be working on these two problems separately. But Alan and I looked at each other and says, why do this separately? It's the same math, for heaven's sakes. Just write one code that does both. And that's what we did. It took us a week to figure out what to call it. And we finally settled on Generalized Structure Analysis System, otherwise known as GSAS. We couldn't call it Structural Analysis System because there already was something else called Statistical Analysis System, which is a software package for doing statistics. So we couldn't call it that, so we had to put the stuff the G on in front of it. Anyway, and so we then spent the next 2-3 years putting that together, and the first version of GSAS that was sort of usable appeared in late 1985 or something. Worked only with neutron time of flight, but did both X-rays, did both single crystals and powder diffraction. And I was looking for a way out of Phoenix because I was becoming very allergic to the air, stuff in the air, in springtime. Phoenix was touted for a long time as being a place where the air is clear and wonderful and, free of everything else that makes life miserable up north. Well, the problem is everyone brought all their favorite plants. And so now this place is sort of this soup of pollen from all over the world. And so I made it known that I would like to move to Los Alamos and applied and interviewed and all that sort of stuff. And in 1986, they said, sure, go ahead. We will hire you on. And let's see, what was it? I guess it was summertime of 1986. But I had also won a Fulbright fellowship to go back to the Rutherford Lab for 6 or 7 months. So they said, go do that first. Well, it turns out that the week that we left Phoenix to fly to England, Chernobyl happened. Okay? And so we were flying on an airplane that had nobody on it for all intents and purposes. And so we arrived in England, spent 7 months there. I worked on extinction problems and some other things. And then I flew back and had my medical examination for the Los Alamos entry, where they do a baseline full body count, find out, what are you coming on board with? And the lady said, where have you been? And I explained, because there's some cesium, whatever it is, in me. And Camille, my wife, accuses me of glowing in the dark anyway. So, having been at Los Alamos. And I guess, so this period in Los Alamos, somewhere in the middle of this, well, in other words, GSAS is sort of developed all the way through all of this, including sort of high pressure work and the texture analysis and protein stuff in sort of the late 1990s. And somewhere along in there, I said, what would a protein pattern look like? And so I simulated what a powder pattern would look like, assuming that the peaks would be sharp or something like that. And I just did that because, what else? Just guessed that they would be sharp. And it looked suitable. It looked like something that would happen. So I asked around at Los Alamos for a small protein, please. Anything that's really, really small. A few hundred atoms, please. Nothing bigger than that. And one morning, I found this little glass vial on my desk with some purple glop in it. And I said, this one. And I sort of asked around, particularly I asked Benno Schoenborn, who was the protein crystallographer at Lance. I said, did you leave this on my desk? And he says, yes. And I said, well, what is it? It says metmyoglobin. Now, if you don't know what metmyoglobin is, it's the stuff that makes red meat red. And by the way, it's also the stuff that makes red meat brown. When the oxygen leaves, it gets replaced by carbon dioxide. That's what makes the hamburger turn brown. CO2 on metmyoglobin. And he said, I asked him, says, well, how many atoms? He says, 1,800 or whatever it is. I said, oops. So then I called Peter Stevens. And first of all, I said, Peter, are you sitting down? And I said, because I have a really crazy request. And that is I want a day's worth of beam time on your powder diffractometer, which, by the way, it was a diffractometer in a phone booth.
Worse than a phone booth, because if that car came down
short, to look at a protein powder. And so I went there, ground the samples as he was describing, and put them on the beam line And I'll show a picture of what that first pattern looked like. But it came back with spikes, basically. There was no broadening to the peaks. They were basically as sharp as you could possibly imagine pattern diffraction peaks looking. They're sharper than the NBS standards, as you would. And I collected this pattern, and I said, what am I going to do with this? This cannot be ignored. I have to do something with it. So then I immediately started working on GSAS to get it to read, use, and fit via read belt refinement protein structures with that data. So I had to implement all this stuff about strengths and whatever it is, put it all into it, and learn a lot about protein crystallography at the time. Anyway, sometimes events, so that was sort of right in here at the same time I was working on Hippo, trying to put it together, which Rudy Bank talked about, and Sven also talked about it. And that was sort of right here around 1999, 2000, thereabouts, something like that. And that was the same time that we learned that my wife had hepatitis C. And so in 2002, we pulled up everything and left to go to Chicago to be near to the University of Chicago hospitals where we would anticipate the transplant being done. And the transplant happened late 2002. I mentioned to the folks at Argonne that, the doctors say it would not be wise to go back and live at 7,500 feet. And they came back a week later and said, "You want a job?" Just like that. I said, yes. So that was the move. That precipitated the move from Los Alamos to Argonne. And that's what I mean by sometimes events like that are what actually drives how you change, what happens to your careers. Anyway, the one thing that's important about this period in Los Alamos is that it was a collaboration between Alan Larson and myself that wrote GSAS. Alan taught me a great deal about FORTRAN. One of the things that we realized almost immediately is that we could not simply trust the users to be able to fill in the control file by hand. So we had to write an editor that would fill it in for them in response to questions and answers and stuff like that. And one of the principles was never ask the same question twice. In other words, if they tell you what the space group is, don't come back and ask them for the space group again because you're going to run some other program. Things like that. So we built this editor that would do that kind of thing. It's all menu driven and everything. People have shown snapshots of it. And one letter responses for all the menu items occasionally required a bit of creative abbreviation, so let's put it that way, so that the keystroke would actually mean something to somebody. But anyway, that's how that got developed. And as I said, at the beginning, it was, you send me a tape and I'll send you back the code on a tape, 6-inch, the small reel is not. And then eventually that sort of evolved to being TK50s, which is the cartridges that you might get. It was originally written for a VAX, and the control file is the so-called ISAM structure, which is a key and then data for each line. And somewhere in that process, I said, let's get this to work on Unix, because someone gave me a Silicon Graphics display station. So I got it to work on Linux, and I had to emulate that ISAM structure and do it. That's what I did. And that, of course, led to a PC version because it was sort of easily translated back to Microsoft's FORTRAN. And that made distribution easier. It opened up the user base a whole lot more because there's a lot more PCs than there are boxes.
Especially now.
Especially now. So anyway, that was sort of the progression of how that worked out. And over that span, which was from about, what did I say here, about 1985 to 2004, the GSAS thing was sort of developed continuously as stuff was added to it. It shows the impact of how our knowledge of peak shapes changed for both constant wavelength and anchor-time flight as things were added on, peak shape functions got stuck in, whatnot. And then at Argonne, my appointment was half IPNS, half APS. And in the beginning, I basically did nothing for APS and everything for IPNS because they wanted me to run the SEPD power diffraction instrument. And that was basically a full-time job. But somewhere in the middle of that, Brian and I sort of recognized, Brian had already written the XP-GUI interface stuff. He had recognized that, and I had recognized that GSAS was sort of the end of its lifetime for development because we were running up to design limits that were built into the software. There was, 99 histograms Alan and I thought that was infinity. Okay. And it turns out that's not true. And 9 phases was extravagant. And people saying, well, I want 15 phases or whatever it was. So anyway, we sort of changed, Brian organized this workshop and somebody gave a picture of it. Of the participants, including Bill David and other folks from Europe, come over and talk about what new software ought to look like. And a white paper was written, submitted to the Department of Energy, and probably wound up, who knows what. Yeah,
I felt no idea.
it was roundly ignored. Somewhere in there, we had heard about this short course in Python taught by the folks at what the organization was. But Brian and I went to Texas, to Fort Worth, to learn about Python. So we spent 3 days learning, quote, scientific Python. Came back saying, what are we going to do with this? And since there was so little response out of anybody about funding or support or whatever, I just said, the heck with this, let me just get started. And I just started writing Python code for what is now known as GSAS-II. Organized the all the array structure and everything else. Just wrote it all out, and got it sort of semi-working. And somewhere along the line, I asked Brian to sort of come on and join me in this little effort. And that's where GSAS-II came from, which was basically sort of in around 2005. And I'm still working on it. Finally, we get to 2019, and the folks at Rutherford wanted me to come back to do some work for them. And Argonne National Laboratory, in their infinite wisdom, said, we won't let you go because this work you could do here. Seriously, that's what they said, told me. And I said, I can't do it here. They're going to pay me. So I retired. So we went to Rutherford, stayed in a place in North Oxford called Summertown, which was about 100 yards from where I stayed in 1972. Literally, just down the street in my home. Thoroughly enjoyed it, saw great things for about 4 months or so. I would drive my rental car down the A34, back up the A34 every day to get to the Rutherford Lab in North Oxford. And you think about horrible traffic. That is the busiest 4-lane highway in England. There's that little stretch of A34 around Oxford down south. But I did it every day. And sort of we get to and what Camille was doing was flying back about once every month or so to tend to her business as a therapist, meet with her clients and so forth. And so in February of 2020, I guess that's right.
Yes, 2020.
2020, she calls me up and says, well, I'm not coming back. There's something going on. Airlines are canceling flights. And in fact, our flight back, the expected flight back in the end of April had been canceled. So I said, okay. About a day or two later, the Rutherford Lab people said, don't come in anymore because we're closing the lab. Because it was COVID. And Camille had then changed my flight to be a particular day, about 3 days hence from that, and that got canceled. And it was rescheduled to sooner, that got canceled. Finally, I went on to British Airways and managed to get on a flight the next day, scrambled to get to Heathrow, which was a very strange experience because driving from Oxford to Heathrow is normally through a lot of heavy traffic. There was no one on the roads, no one at all. We were just about the only car on the road driving down to Heathrow. Heathrow was really kind of odd, as you might imagine. There was no social distancing because nobody figured that kind of stuff out yet. And landing at O'Hare was also weird because they sort of filtered us through this little inspection station where they took your temperature and said, yeah, you're okay, but quarantine for 14 days anyway. Yeah, really very odd. And so I got home and lived for the next 2 weeks in the basement. Was my version of quarantine. And eventually sold our house, moved to Arizona briefly, because our house sold in a day rather than spread over several months. And we were homeless, so to speak, and looking for a place to live. And finally found a place about 2.5 years ago on the lake. Anyway, so that's the history. Kudos, colleagues and collaborations. This is just a short list, it's a partial list. It does not include everybody. And if your name's not on there, don't be offended. I'm just going to get around to putting it on. But the people I want to point out in particular is Professor Fay, who basically taught me how to write scientific papers and articles and GSAS-II GSAS manuals and things like that. That's kind of stuff that he taught me how to do, as well as the science of doing synthetic inorganic chemistry. Hughes and Hoard were the crystallographers at Cornell. Of course, they taught me whatever crystallography there was. Ed Costner was a synthetic inorganic solid-state chemist who made some of the stuff that I've looked at, was doing single crystal work there. John Staszowski, Victor Day, and Bob Scheit, and there's some other people too, were postdocs doing crystallography in Hughes and Hoard's laboratory, some top floor chemistry. Then moving to Arizona State, faculty members that sort of interacted with were Professor Leroy Eyring, Mike O'Keefe, Peter Busick, who Jeff Post worked for. Ted Brown was an synthetic inorganic chemist, and I did a number of his crystal structures. John Spence was in physics department. Alex Navrosky was geology, chemistry. John Holloway is the same way. John Holloway did high pressure work. Bill Glausinger was a graduate student at ASU, and then he went, at Cornell, and then he went to ASU about a year after I got back. And Ray Young, of course, at Georgia Tech, Jeff and Gene Peterson was a graduate student of Ted Brown's, and did a number of crystal structures with him. The one thing I would say about Ray Young is that he organized these Wheat Belt workshops and he went out and got funding for them from the National Science Foundation. So that's how we got our airfares and whatnot paid to go to places like Poland, South America, and Russia, and so forth, to teach people how to do Wheat Belt refinements. And we called it the Wheat Belt Refinement Roadshow. Tony Cheatham, Ray Young, and myself went around to these various places teaching people how to do this stuff. And at Oxford, of course, is J.S. Anderson, Tony Cheatham in particular, obviously. But there's all these other people who were there one time or another, and this is where I met Hugo Rietveld himself. But he came over for a visit or something. Exactly what the situation was. And then going back to the Rutherford Lab, it was Andrew Taylor, Mike Johnson, Bill David, Colin Windsor, Alan Hewitt, people like that. And at Los Alamos, of course, is Alan Larson, who was my collaborator writing GSAS. And Richard Silver, who was the group leader to do it. And then there were other people who were group leaders, people that I worked with, Dave Fish, people doing protein single crystal stuff like Bob Blessing, which was at the Hopman Woodward Institute in Buffalo, Peter Stevens, of course, and other folks for all the sorts of things that we did, including this person here, Sergei Stishov. Now, you may wonder, who the heck is Sergei Stishov? Well, he's a Russian, and he's the guy who synthesized what we now call stishovite, which is SiO2, but instead of being tetrahedral silicon, it's octahedral silicon. It's a high pressure phase. And he was a very interesting character. Hans Bugge is the guy who sort of set me on texture analysis, and it's his book that has all the mathematics doing that sort of stuff. At Argonne, obviously Brian, but there's other people like Jim Jorgensen, Jim Richardson, Kristen, Jennifer Doubler, who was a postdoc with me, and then other people who I visited in various places when they were at the ESRF. And as I said, many others. And Peter Lee, by the way, who helped me with some of the first powder patterns that I was able to collect at APS. APS is a little bit of a problem compared to NSLS. My samples would get fried far faster than they would at NSLS. Okay. Next. There we go. Icons and pictures. Here's Hugo Rietveld standing by his instrument in the Netherlands. Here is the manual written by Alan Hewitt of the original, his version of the original Rietveld FORTRAN code, which is what is then the basis for all the rest of them. I put this up here because what's in the background is an 8x8 core memory, which was on the kind of computers that we were using back in the 60s. And what's sitting on the top of it is an 8 gigabyte chip, which is a modern one. And that demonstrates the evolution of computing while I was doing my work. That really says it all about how the science has progressed, because without that, the stuff we do now would not be possible. Literally not possible at all.
Thank you.
I have here the two logos for the GSAS and GSAS-II. This one I simply put together using balls and sticks and something like that. Just get something so it looks like a logo. This one's an interesting little molecule, which is for GSAS-II. It's a real molecule. It's pentaerythryl tetranitrate, otherwise known as PETN, which is high explosive. And when I was at Los Alamos, I did a high pressure experiment on PETN. I did two of them. The first one ended with a bang, because I had gotten a little bit of PETN stuck in between the gases. The second time, I actually managed to recover the sample after getting it up to around 10 kilobars or so. And what was interesting about it is that as you increase the pressure of the molecule, it does a slow rotation by 20 degrees or something like that, which makes it more sensitive to a shock wave. That's why it explodes. There's Hippo. This one is the first X-ray powder pattern protein of that myoglobin. And as I said, when those peaks started coming out, like this, as we could see them, as the numbers would go like that, and we said, wow. That's all we could say. And here's a little sketch of the two zinc insulin molecules. One's rotated around 9 degrees relative to the other, but I managed to solve the crystal structure. It was a 3-parameter problem, which was just simply how far apart they were and how much one was twisted relative to the other. This is, with the help of Peter Lee, a powder diffraction pattern of lysozyme taken at 1 BM at APS on an image plate. And there's 8,000 lines in that powder pattern between there and up there. The image almost doesn't do justice. You kind of see them here. You may wonder what this is. Well, this is tracking the phases of the few reflections during charge flipping. And you notice that on this side, they're just all over the place. It's chaotic behavior. And then suddenly, it snaps into place, and then you just get simple oscillation in the phases. This is chaotic behavior. And if you look at the charge flipping algorithm, it's a loop with 2 legs in which some modification is done. And then there's 2 Fourier transforms. So it's Fourier transform, modify, Fourier back Fourier transform, modify. And it goes around in a loop. And that's characteristic of any chaotic process, is to have that kind of a loop. And so this is basically a hyperdimensional version of the chaos sort of stuff. And the solutions to charge flipping solutions then are strange attractors. Who knew? So all the behavior of charge flipping can be understood in the context of chaotic behavior. This thing is the thing that Charles Lake showed, which is the McGovernite. This thing is, you may not have noticed, but this is 203 angstroms along that z-axis. And this is the charge flipping solution. It basically shows almost all the atoms in the structure. Some 700 odd peaks in there. Let's see what's next. Not much more. Hello.
Pointed at the computer.
There we go. Let me see. I talked about that. I talked about this briefly. The only thing I want to say about this one is that one of our responsibilities as instrument scientists at Los Alamos was to go across the street where the operators met every morning. One of us would go over there and tell them what it is we were doing that day. And so I walked over when I was doing this experiment and did my turn. And they asked me, this is what we were doing. He says, well, I'm doing an experiment at high pressure on a high explosive. And they just laughed. And then I said, if you hear something that sounds like a gunshot, don't worry, it's just me. Because it literally is what you get when these things let go. This loud bang. Talk to you about that. Metal ammonia experiments. A couple people have sort of touched on this, but what we had to do was we did these at Los Alamos at the reactor. And to do them, we had to make them. Bill Glousinger had to make the samples, deuterated ammonia and some metal, whatever it was, calcium, sodium, lithium, whatever. And we would then carry these things in glass vials, immersed in liquid nitrogen up to Los Alamos, around 9-10 hour drive, whatever. And as he said, he would make these funny noises. And the other thing I want to add to that is you may wonder how we got rid of them. Well, we just simply took the sample and put it in a coffee can that was outside the back door and went off to lunch. And when we got back, it will have exploded. And a little fire in there. The kind of stuff you couldn't even think of doing nowadays. But there wasn't any other way to dispose of them except by doing it. Jeff talked a little bit about the astronomy. The only thing I could add to that is that I indeed did make 2 mirrors. One is the 8-inch one and another one's a 6-inch one. And that is actually an amazing experience, grinding and polishing a telescope mirror that is roughly this big around, all by hand, no machinery, nothing like that. And you use a little thing called a Foucault tester to check the curvature, because you have to appreciate that it's not a sphere, it's a parabola, in order to get proper focusing. And by the way, I was doing this at about the same time that they discovered that the Hubble telescope had been misground. You may remember that, okay? And I said, how could you possibly screw that up?
Focusing on the wrong spot.
Was that?
They were focusing on the wrong spot.
They were focusing on...
There were 2 spots and they picked the wrong one to shape the focus.
Yeah.
So it was perfectly imperfect.
It was
which is
perfectly
good,
imperfect.
because then you can put a pair of glasses on and make it perfect.
Yeah, right.
And the Hubble's still working.
Exactly. So anyway, and by the way, the person that's sort of talked about making these kinds of mirrors is a fellow by the name of John Dobson. He was an old, craggy old guy when I met him. And he came and visited Los Alamos one time in the middle of the winter. And we did a star party afterwards. It was a little cold and whatnot, but the skies were spectacular. And he actually looked through my telescope. It was kind of cool to have the guy who invented these things look through your own telescope. He had a few suggestions about how to improve on the telescope. So, and finally, you may wonder what I do. as a hobby, and I build model ships. And the next picture actually shows a couple of pictures.
If I can get it to do it. Hello, there we go.
That happened.
Oh, there we go.
This one is the U.S. brig Niagara, which was Commodore Perry's flagship in the Battle of Lake Erie in 1813, which he beat the Brits for the control of the Great Lakes. That's why U.S. owns the Great Lakes. This is all made from pieces of wood, strings, ropes, if you like, little bits of cast iron for the cannon. Lots and lots of detail that the pictures don't even show. You really can't even see it. Every one of these ropes worked at least once as I was putting it together, because you have to adjust them and then move them. This one, of which I have one mast with sails on it, and then there's two more masts, is HMS Victory, which was Nelson's flagship at the Battle of Trafalgar, which would combine French and Spanish fleets, thus prevented Napoleon from invading England in 1805. This guy has 20 cannon. This one has 100. This is a really big boat compared to that one. There is a replica of this in Erie, Pennsylvania, which you can actually go visit and walk around on its deck. This one, the original, is still in Portsmouth, England, and you can get out and walk around on its deck and see what it looks like. I have seen both of them. This is a view out my office window. One of its common. And finally, oh, here's some more pictures of paper. All sorts of detail. Finally,
There we go.
I need to thank two people. One is Veronica, who unfortunately died 20 years ago yesterday, and Camille, for inspiration, love, etc. Thank you all.